Well, thank you very much for the presentation, Professor Ferreira. And also, I would also like to thank the organizers for inviting me here to share the work we've been doing these last few years, and which Antonia already started presenting. So my presentation is a little bit of a continuation of what she just showed. So just to summarize a little bit, although some of these have already been said here, when you want to reconstruct or repair bone that has been damaged, there are several options, and the main one used by the one preferred by doctors are the use of grafts. And grafts is basically bone tissue coming either from the same patient or from donors or even some animals. But these, even the gold standard, which is autografts coming from the same patient, they have their own problems, because basically you are very limited in the amount of material you can take from the patient. And also, because you need a second surgical site, there is additional morbidity and problems associated with the use of these materials. And even when you take the material from a donor, you are also limited a little bit on the amount of material that is available, and you face other problems like rejection, immunogenic response from the patient, and also you have risks of transmission of diseases coming from the patient that donated the tissue. Solution to all these problems is to resort to biomaterials, artificial implants that can be used to replace the bone that has been damaged. And the problem with all those materials, which are, as you said, in first generation, basically bioinert materials like metals and ceramics, they are too rigid. The mechanical properties are very different from bone, and that produces a problem which is called stress shielding, where basically the bone surrounding the implant doesn't support any load, and this absence of loading of stress in the tissue prevents bone or stops bone remodeling. So basically you will start losing more and more material, and eventually your implant will lose fixation, and you eventually have to replace it and remove it. And this is a problem, of course, for the patient, and also in terms of economical impact of these solutions for the healthcare systems. So, as Antonia mentioned, we need materials that can substitute bone but have mechanical properties that are close to natural bone. We would like the material also to be osteoregenerative, so it should help bone remodeling and repair by their own cells. And it should be resorbable, so it should disappear once the new tissue is in place. And of course, we would like to be able to shape these materials into the patient lesion so it fits perfectly. And so how do we do that? Antonia already mentioned that porous, bioceramic, and bioglass scaffolds are very good solutions in terms of osteoregenerative properties especially, but they are all brittle. And for the shape customization and the optimization of the mechanical properties, using additive manufacturing makes a lot of sense, because we can optimize the porosity to improve mechanical and also osteoregenerative performance. And also, we can customize the implants. We can take medical scans, use it to fabricate a 3D model of the implant that we want to place, use 3D printing to produce those implants, and then those implants will perfectly fit the patient lesions, which is something we would like. And also, we can even add elements that help doctors implant the material, like anchorage elements that will help the whole process. So when it comes to additive manufacturing, Antonia has already presented some of the work we did with robocasting, which is a material extrusion additive manufacturing technique. But there are other families of 3D printing. And what I'm going to present today, it's related to another one, which is called digital light processing, which belonging to the family of bath photopolymerization. And this process basically consists on projecting light into a bath, a container with photosensitive resin that will photocure when it's heated by the light, and this produce a full layer on a single step. So the speed for printing should be high, but also because the size of the pixels that we can project with UV projectors are very, very fine, so the resolution of these techniques is higher than that of robocasting. Of course, you need to use for that photosensitive resin-based feedstock materials, usually very low viscosity resins. So in principle, it's a technique for polymers, but you can actually print anything as long as you can produce colloidal suspensions of those materials, powder from those materials into these polymeric resins. The difficulty here is to keep the low viscosity that is needed for the printing process, because the printing process goes like this. You project the light and cure a single layer, then remove, put back your materials, and let the suspension go back below the sample. And for that, you need to have a very low viscosity suspension. The key here is to match the curing depth of the light, so by adjusting the exposure and intensity of the light, so that the cure depth matches the layer thickness that you have selected. And if you do that, then you layer by layer build your material. The layer thickness, after printing, you take the sample out of the vat, and you may have, if you have pores especially, which is the case in the case of a scaffold, you may have some resin trapped in the pores. So you need to do a thorough cleaning process using typically sonication in isopropanol, or maybe using blowing air through the pores, trying to remove any traces of this residual resin. Afterwards, you sometimes use some post-UV curing in a UV chamber. And then, if your material is not the polymer itself, but you want to produce ceramic, as typically in our case, you need to do a heat treatment later on to remove the resin, the photopolymer, so that we call that the binding process, which it has to be very slow to avoid any cracking. And then you elevate the temperature to the sintering temperature for those powders that you are using. And final dimensions of your material will be controlled by the model that you use, the printing parameters that you are selecting, and also by the shrinkage occurring during the binding and the sintering process. Another thing that has to be taken into account when using DLP is, and when you are using ceramic powders, for example, or any other type of powders in suspension, is that the particle will also scatter light, so there will be a deviation of your part from the size that you selected in the model, so from the image that you are projecting, because light will scatter around each of the pixels. Okay. Nonetheless, despite if you take into account all those issues, you can produce nice bioceramic scaffolds, as I'm showing you here. You can see that there's a large shrinkage between the green body and the sinter structure. And also, you can see the actual individual layers of the printing process on the external surfaces of the scaffold. And one of the things that we found out, it's very complex to do very fine, very small small pores, because when you do that, as you see at the bottom here, when you reduce the feature of the size of the pores, you start getting an increase in density, even though we designed this scaffold to have all of them the same density. And the reason for that is that you are not actually able to remove all the trapped resin from the scaffold. So at the center of those scaffolds, some residual resin remains, and during the sintering process, it becomes part of the scaffold. So it blocks the porosity, which is a problem. So you don't want that. Okay, so that's a limitation. In principle, DLP has higher resolution, so you could go to smaller pores, but in fact, you are limited in the size because of this problem with the trapped resin. What about mechanical properties? Because as Antonia mentioned, that's our main goal, is to try to produce a scaffold with improved mechanical properties. And as you can see, the compressive strength of this scaffold is comparable to that of RoboCast structures, but there is a twist here, and there is a difference in the mechanical behavior depending on how do you load those structures. They were supposed to be symmetric in all directions, but when you test the scaffolds, if you test loading parallel to the layers that you have deposited, your material has a much higher strength than compared when you test it perpendicular. And the reason for that is that we observe this hourglass shaped cracks, which is typical of laminate materials. And this means that the cracking is occurring by a shear process, and this means that there must be some defects in between each of the layers that you have deposited during the printing process. Although we are unable to see those defects, though they must be there, okay? If you see, you can see the steps on the surface, but there are no actual line of defects aligned with each of the interfaces. So bonding seems to be good, but still there must be some defects producing this shear cracking, okay? But the main problem of scaffolds produced by DLP is not strength, it's again toughness, okay? As Antonia mentioned, these materials are very brittle. Even cortical bone, which is the most brittle part of bone, it can sustain an amount of deformation before actual complete failure. Whereas in our case, we have this abrupt drop load. That means the material is completely fractured as soon as you reach the maximum stress. So that's not good. We need to learn from nature, and we need to try to produce biocomposites. That's how bones does it. I mean, properties of bone arise by mixing two materials that are relatively weak, either in terms of stiffness or toughness. But when you combine them into a composite, okay, we can have the properties of bone. So we are not the first, and will not be the last to try this, to do composite materials for bone regeneration. But instead of using polymer matrix composites, we are trying to produce materials in which our ceramic material is a matrix. It's a continuous phase. So Antonia mentioned already that we can produce that by polymer infiltration. Either we get full dense structures that can still be used as scaffolds, because if you select a polymer which is biodegradable, you could produce the porosity in situ. That's possible. And nonetheless, even if they are not scaffolds anymore, they could still be used for fixation devices, which are dense. So that's another possibility for using of the fully impregnated structures. Or we can preserve the porosity and get only coatings that will heal the defects on the struts, but also keep the macro porosity that we defined, will preserve it, so we can still get bone growth and so on. But the problem, when you come to, well, and this, as already Antonia mentioned, we improve the mechanical properties both in terms of strength and toughness, both in compression and bending. I'm not going to stop here because she already did a very good job presenting all that. But I wanted to mention the main drawback of what she did, which I almost expected to arise during the during the questions, is that what happens with the biological performance. Okay, in the case of fully impregnated structures, we are losing the porosity, so no bone growth. But even in coated structure, or even in fully impregnated structure where the porosity is created in situ, you will still have the polymer on the struts. And this will isolate the good bioactive properties of these ceramic materials, of calcium phosphates or bioglasses. You will not, the cells will not know because it's already covered with a polymer. So that's a problem. You are losing bioactivity. You have no osteoconductivity, no porosity in the case of fully impregnated. So how do we solve that? And we thought, okay, maybe we can still have the polymer, so we have a composite, but keeping the polymer far from the surface of the ceramic material. So we started trying to produce structures like these ones, in which we have the biopolymer inside the struts rather than on the outside. So these coaxial structures, we will still show an improvement in toughness, that's what we expected, and will preserve both the porosity and the osteoconductive capacity of the material. So how do we produce those type of structures? Well, we will be using the high resolution of DLP to produce structures of ceramic material which are hollow. The struts of this material will be hollow, so we will have two sets of porosities, the one on the outside of the struts and the one on the inside, the channels. And we were producing two types of structures, one which is similar to the Robocast structure, in this log pile structure, but with channels inside. And then the one that I'm showing on the right, in which the channels are interconnected in the three directions of space, because the struts form an interpenetrated network. Once we have this printed, what we do to incorporate the polymer is simply infiltrate the channels, the internal channels, by using a suction method. We put some inlet and outlet in our scaffold, and then by applying a vacuum, we suck a polymer melt inside those channels, and we fill these internal channels with the polymer. And we did that, and in fact, as you can see on this slide, we were able to produce those structures. You have the dense struts, hollow struts, and then at the bottom you have the hybrid structure, in which we have the polymer, PCl in our case, filling completely the internal channels of these scaffolds. What about the mechanical properties of this material? Well, we tested that using two different configurations with two different sizes of the internal channels. So some of them with 40%, occupying 40% of the struts, some others with 60%. And as you can see, there is you can already see on these stress strain plots that there was an increase in the toughness, but I will try to disclose this a little bit more slowly. So what happens when we go from the dense struts to hollow struts? Well, as you can see here, there is, of course, as was expected, a reduction of the strength. And that's simply because you have less material to support the load. So each of the remaining material has to withstand more stress, and therefore the final compressive strength of the material is going to be reduced. But the good thing that we found is that once you fill those internal channels with the polymer, even a weak polymer, a relatively soft polymer like PCl, you recover most of the strength you lost by going to hollow struts. So that's good in compressive strength. There was not much, but the main important feature that we wanted to get was not strength. We weren't expecting an improvement, of course, in strength, rather what I showed, a reduction of it. But the good thing is that we did get what we wanted. This is an increase on the toughness of the structure. Okay, is after peak load, we still can sustain load for a long time. Even after large strains, you can still withstand some load, which is exactly what we wanted. And you are not sacrificing here neither the porosity nor the osteoconductive properties of the material. Okay, so we get the toughening we wanted without losing biological properties and performance. What we also found is that you almost get no difference depending on the amount of polymer you get on the inside. So it doesn't matter too much if you have a very large channel with a lot of polymer or rather a smaller channel. So in principle, and because, as you can see on the plots, there is a slight decrease with when you increase the amount of channels on the strength of the hollow structures. So the advice would be, okay, put some polymer inside, but not put too much, just enough to have the mechanical enhancement in terms of having these polymeric fibers joining together the struts even after they fail. So a small amount of polymer inside the struts is enough to get what you want. Okay, so what happened about the other structure I mentioned, the one where you have full interconnectivity between the internal channels of the structures? Well, the advantage of this configuration is that this toughening that we have will be more isotropic. Okay, because on the block pile structure you have polymeric fibers only on 2 directions of a space, while in this structure you have them interconnected in the 3 dimensions, so it doesn't matter how you load it, you're always going to find polymer opposing any crack bridging and any crack propagation through the structure. So this is a better option in terms of having isotropic reinforcement of the material. And a real good reinforcement in terms of toughening of the material is achieved, even in bending, under bending stresses. And as you can see here, you see the typical brittle behavior that you see on the dense and hollow struts, this sudden drop, and as you can see a catastrophic failure of the material in bending. They just pop out. You see them breaking in milliseconds, and that's it, they are gone. Your material is no longer useful for anything. Whereas when you have the polymer on the inside of the channel, even long after initial failure, you can still withstand the load. Okay, this material has been, the one on the right, has been tested for a very long displacement. So you've been stretching those fibers for a long time, and still your material is in one piece. Okay, the ceramic is broken, that's for sure, but the material still sustains some load. So that's what we wanted, and we get it. And the amount of strengthening that we observe, well, no strengthening, sorry, as expected, because basically we have the polymer on the inside, and on bending, the material is breaking from the outside, so polymer is not doing nothing there, so strength remains the same, but we do get a very substantial improvement on the toughening. And we have a more than 1 order of magnitude improvement in the toughness and the strength energy density, which is basically a measurement of toughness in the material. So that's what we wanted. This is a very good solution for that. And as you can see here, those are some of the results that Antonio already mentioned, and the materials that I'm highlighting there are the new ones with the coaxial structures. And as you can see, we have improved the toughness. We have materials that are tougher than dense strated structures, but without sacrificing biological performance, nor strength. Strength is still more or less the same as the dense structures, which is pretty good. And we are improving toughness even over coatings. Okay, coated materials, they do not produce as tough structures as we can produce with this coaxial strategy. Of course, we are losing some of the strengthening that we had when we had the coatings. There is no longer any polymer on the outside, so no defect healing, so the strengthening is lost, but the toughening is better. In fact, the toughening is so good that it's as good as when you completely fill the structure with polymer, even losing the whole macropores. So no, we are having not the strengthening that we had in that case, but we have the toughness comparable to that of those structures. And we, as you see, we are relatively close to toughness of cortical bone, even in bending, which is very, very difficult. Okay, so we are almost there. Of course, a lot of work to be done to keep improving this, but this is a suitable strategy that may allow us to have materials that are both osteoconductive, osteoregenerative, and also tough enough to be used in load bearing applications, which is, of course, not all bone defects require this, but definitely this is something that is required in some applications. Okay. And finally, just to complete my presentation, I'm going to show you some other things that can be done with DLP, and in which we are currently working, just starting, so not much that I can show you, but some of it. I can give you a gist of what we are doing. It's trying to use DLP to reproduce materials for dental applications. Briefly, when you lose some of your teeth is damaged by use, it's typically the most external part of the teeth, which is called the enamel, that is lost, that is broken. And this enamel is the hardest tissue in the body, but it has a drawback and it's one of the few tissues in the body that doesn't regenerate at all. Okay, so once you lost it, it's gone. And what you do, what you can do, the doctors can do, the dentist, is basically replace this external part of the teeth that has been damaged with a crown or a veneer, which is basically a ceramic materials, a very hard and brittle ceramic materials, which is put either on top of the remaining teeth or some implant, and it's put on the outside. And even though these materials are much harder, much stronger, and stiffer than the initial enamel, they still fail. And they still fail because of the same thing we've been telling you, Anthony and me, in our two presentations, is because they are too brittle. They just break, and that's it. That's the end of the story. So we need materials that are tougher for this type of applications. So how do we do that? Well, the idea that we are trying to develop is trying to mimic nature again. So what's enamel? How is enamel? It's a biocomposite, again, of hydroxyapatite and collagen. It's basically the same thing as bone, just in a different configuration. Much more mineral phase. And basically, the high mineral phase is in the form of rods that are very close together and joined together with a low mineral content phase. Sorry, yeah, I'm finishing. It's just two slides. So how do we do that? So we are trying to produce by DLP ceramic rods, by additive manufacturing, and then infiltrate these rods, the interface between the rods, the gaps between these rods, with a polymer, similar as what we have been showing you in these two presentations. We are trying to do this in two ways. By indirect DLP route, we produce a polymer template. We submerge the mold in the ceramic suspension. We fill up with ceramic, and then we heat treat the whole structure, and we get the rods. Unfortunately, this is proving very cumbersome and very difficult to do because the debinding and the burning up of the resin initial mold is producing cracks. So we has only been able to produce relatively large structures around the millimeter scale, so not good enough. So we are trying to do the direct DLP route, in which we have either ceramic resin suspensions or pre-ceramic polymer resins, and then we print the structures, and as you can see there, we can produce features below the 100 micron range, okay? And although this is still in progress, we still have to optimize the sintering and the infiltration process later on with the polymer, but preliminary work that we did already with robocasting structures show that these materials, when we infiltrate with polymers, they do have a resemblance to enamel, and also show what we want, some toughening. Okay, as you can see, fracture surfaces on these structures, even with this polymer that we use here, which is epoxy, which is very brittle, they still show a rough surface for the crack, which means we are having some toughening effects. And indeed, when you show biaxial fracture done on these structures, we also show that these biocomposites, they exhibit a lot of residual load-bearing capacity after the peak, after fracture. Okay, so these materials will exhibit a much better performance than conventional dental materials. This Vita and Lava, those are two conventional dental composites. They are already composites, and they're still brittle because they have a large amount of ceramic, and they show a typical brittle behavior. In our case, we don't have this brittle behavior. We have a tough material, even using relatively unoptimized structure and materials. Thank you for your attention, and I'll be glad to answer any questions. Thank you.
Thanks for this interesting presentation. Please.
Can you say something about the degradation speed of the polymer that you're using? So the polymer that you're using are hydrolytically degrading polymers.
Yeah. They are basically low degrading, that's true. This is a model system. We are more focused on optimizing mechanical property than actual biological performance. For the materials that I've been presenting where the polymer is on the inside, that's not a big deal. They can be there for a long time. Even if they take 2 years in degrading, that's still okay. As long as they are gone, eventually it's fine. Of course, when you are talking about fully impregnated structure where you want to create porosity in situ, then you would like to have a faster degrading polymer, filling those gaps. But we haven't done much on that.
That is not really what I'm aiming at. What I'm aiming at is that if you get degradation of your polymer, you get a very high level of acidity.
Acidity. Oh, yeah.
And that will also affect your ceramic.
Yeah, but not significantly. We have done some degradation in vitro, okay, in the lab, and mechanical properties do degrade, but they take months. So it's on the range of what you will. I mean, it's on the range of bone regeneration times. So it's not a big deal.
Well, I think it's time for moving to the next one.
Okay.
But before this, I would like to. You are proposing something composite for kind of crown, which is, let's say, why do not think about zirconia, for example?
Oh yeah, that we are definitely doing that. Yeah, in fact, this was made with hydroxyapatite and epoxy, but what we are doing here, right there, it's going to be done both in alumina and zirconia, as well as TCP. So we may have biocompatible materials, but also bio-inert structures. Because in the case of dental application, it's true. Strength is more important, so probably going to the strongest ceramics makes sense rather than having biocompatibility, which is not a big issue in the mouth.
Thanks again to the speaker for the presentation. And the next one. And last of this section is Michaela Maizescu, and comes from Romania, Department of Biophysics and Cellular Biotechnology, Faculty of Medicine, University of Medicine and Pharmacy in Karol Davila. So the title is already there, so please go ahead. Thank you.
Good morning. And it is working, yes. Thank you for the invitation, Georgia. Thank you for organizing such an interesting meeting. I will start by disclosing something. When I arrived yesterday, I had a feeling that I'm a child invited to the grown-up playground, you know. We are new in the field. We are at the beginning. We are a small group, but we are enthusiastic. So I hope that I will compensate with this. But still, my presentation of today will be about some biological tests that we done on some nanoparticles. It's not us that produce the nanoparticles. You'll see later on. But we tried to figure out some methods that may produce interesting data. In general, we know that the nanotherapeutics have been shown already that they are bridging the biological and physical sciences to the medicine in terms of producing nanoparticles which are overcoming the limitations of free therapeutics, like, I don't know, low solubility or not so good penetration. The idea is that the nano-sized nanoparticles are commonly used today for drug delivery. Yeah, it's not that okay, but not only for tissue engineering, for theranostics, for some imaging tools, as an imaging tool, and there are classical classifications taking into account the chemical structure of those nanoparticles with specific advantages or disadvantages For instance, the polymeric, the possibility for having aggregation, or for the inorganic, quite sometimes toxicity, high level of toxicity. In the case of lipid-based nanoparticles, the low encapsulation efficacy. Moreover, there are these attributes which you already know, that the surface material properties, the targeting moieties, the architecture, the possibility of triggering the responsiveness of the drug release. All these attributes can be modified in a way, in an intelligent way, in order to produce a nanoparticle which is useful for an application. Okay, but I'm a medical doctor. I was amazed inside the cell. Okay, I have two cases, like in hospital, two cases to present it to you. A case of the case of nanoparticles with oxide, zinc oxide, doped with manganese. The zinc oxide is known for applications in technologies, in cosmetics, in food packaging, and in biomedical applications, because we are using it for its antimicrobial, even some anti-tumoral properties, anti-inflammatory anyway, this is very well known. And most recently, the nanoparticles of zinc oxide has been introduced into the masks that can be that are mandatory in the clinic, and it has been a discussion with collaborators in Magurele about is it the agent, the structure directing agent, modifying the cytotoxicity of these type of nanoparticles, and the manganese doping is also important in terms of their properties. And Traian Popescu and his colleagues prepared such nanoparticles in zinc oxide with manganese by a co-precipitation synthesis method with different concentrations, nominal concentrations of manganese. You see them here, using two different surfactants. Further on, you'll see these labels for our nanoparticles. And they investigated and characterized their nanoparticles with different methods, and then they sent it to us, to the Faculty of Medicine. And here, Christian, the PhD student, evaluated these nanoparticles using, I will say, standard for you and for methods. The MTS viability, the ROS production, reactive oxygen species production, and the DNA fragmentation degree by using a classical COMET assay. And the nanoparticles were fully characterized by our colleagues from here. So we knew the dimension, the size distribution, the actual concentration of manganese, some textural properties of the samples, all these parameters. And then Christian performed the classical MTS, which you know is the procedure to evaluate as an endpoint test the viability of a cell, in fact, of the mitochondrial enzymes' capability to produce that colored formazan. And she obtained these graphs, which are showing to us that for concentrations below 4 micrograms per milliliter, there was no toxic effect on the growth of NIH murine fibroblasts when they were incubated 24 hours with such categories of nanoparticles in different concentrations. And the toxic effect appeared and started to be statistically significant with 8 micrograms per milliliter. And it was interesting to see that the 50 parts per million presence of manganese slightly decreased in comparison with the other two types of nanoparticles. Even the structure, the surfactant was the same, while and there were no, let's say, important differences between PVP and the other category of surfactant in terms of impacting the cell viability. Then Christian measured the ROS production using attached cells with a DCFDA product, which was, once inside the cell, is producing a compound which is fluorescent. And this fluorescent intensity she normalized to the cell area. So it was a single cell type of measurement, but normalized to the cell area. And she obtained these types of graphs of ROS production with respect to the concentration of the nanoparticle. And we can see that once the concentration of the nanoparticle is increasing, the ROS production is also increasing for both types of surfactants, types of nanoparticles in terms of surfactant. But the higher the nominal manganese doping concentration, the less pronounced was the dependency of this ROS production with the nanoparticle concentration. I put some arrows here in order to be more visible. And this effect, this behavior was more pronounced in the case of Zom's category of nanoparticles or surfactant. And in fact, for the highest manganese concentration, here, you see here that it was practically no more dependence of the ROS production on the nanoparticle concentration. Then, Christian applied classical comet assay. She extracted the DNA and she put it on glass slides, and she performed electrophoresis, and she measured the tail moment length. And of course, when the fragment of DNA is lighter, the faster it migrates, and when it's heavier, this comet is more visible. And she obtained, again, some variation of the tail length with the concentration of, not so important, with the concentration of the nanoparticle. Okay, we are above the values of tail length for the control and below the values for the positive control, because we used some peroxide to break it, this DNA, in order to have let's say the range. And we saw that the PVP formulation, increasing either the nanoparticle concentration or the manganese doping did not produce a further augmentation of the DNA fragmentation. In the case of the SHMTP formulation, this increase of the manganese nominal doping concentration reduced a little bit the DNA fragmentation. And this can be correlated with the fact that in the SMHTP type of nanoparticle, there is an increased doping in manganese, and the manganese itself has an antioxidant effect. Further, we tried to find a way to see where these nanoparticles are going. And for this, we used a system for 1,000 nanometer in each pixel. You can see here, this is an image of the working software window, and you can see here a zoom on a pixel. And here this is a field with a lot of nanoparticles dried on a glass. And this time Luminita, she was in charge of seeding the cells on glass slides to incubate the cells with these two types of nanoparticles, and then to stain them. For the cytoskeleton, we follow it in Alexa fluor. For the nucleus, with DAPI. And to acquire this type of images of dark field and of hyperspectral microscopy. Then Nicolae developed several MATLAB scripts to identify the edges of the nucleus and of the cellular cytoplasm on each cross section of these Z stacks. Sorry, I forgot to say that for each optical field, there were 3 sets of Z stacks that were acquired. One for DAPI, one for Alexa, and one in, let's say, white light to see to have the reflection from the nanoparticles. And then he reconstructed the cell, and he counted in each region and in the whole cell the number of nanoparticles that the system detected, and he marked 4 regions of interest around the nucleus and inside the cellular membrane. Because we know that the nanoparticles are accessing the cellular cytoplasm mostly by endocytosis, and there are deposits of nanoparticles here close to the nucleus where the Golgi apparatus is, and all these vesicle layers are present, and here close to the membrane again. Boom. And here you have some images with such a cell in these 3 categories of Z stacks, and no, but it's okay, even though. It was the 3D image where you can recognize the nucleus, the cytoplasm, and the red dots here are the nanoparticles. And for one category of nanoparticle, for the other one, the nanoparticles are not labeled, yeah? They are read just for us to see them here. And in a hyperspectral microscope, and not, I don't know, a mitochondria or something else. And then we saw that at very low particle density can be found in the nuclei of the cells. Here, almost nothing. It was at the threshold of the method to identify the nanoparticles inside the nucleus of the cell, while a high particle density, the orange bars, were present close to the inside the membrane, let's say, to what we consider to be the edge of the cell. And it was a tendency of nanoparticles density in shell 1, this one around the nucleus, to increase with the extracellular nanoparticle concentration. But not so much variation in case of cytoplasm. For the one concentration, the smallest concentration that we used, 1 microgram per ml nanoparticle, the differences between the nanoparticle densities in the 4 regions, you can see here, are suggesting an endocytosis-driven uptake, which is not, for this concentration, which is not saturated yet. But for higher concentrations, this phenomenon seems to be already reached of saturation. There were no differences between the 2 types of nanoparticles in terms of surfactant. Okay, so we obtained these results, which we very fast used them. In fact, the method, we use it for some other category of nanoparticles. The folate, a folate functionalized silica nanoparticle. I will skip the general idea because it is already known that the folate, the receptors for folate is extended as expression in cancer cells. And some SBA15 silica nanoparticles with folate were produced. And we try to see if this folate functionalization is modifying the efficiency of nanoparticle incorporation and the subsequent intracellular irinotecan delivery. The nanoparticles were conjugated also with a cytotoxic drug, the irinotecan, which is commonly used by us for treating colonic adenocarcinoma, for lung, for pancreatic cancer, either as a single treatment or as a lone drug or in combination with fluorouracil or chemicals filled with irinotecan and covered with folate arrived in our lab. And Luminița obtained an increase of irinotecan toxicity, an important decrease of irinotecan toxicity when the nanoparticle was functionalized with folate on both murine fibroblast cell line, but also on the human colonic adenocarcinoma cell line, CACO2. And this toxicity was increased for all types of incubation times that you can see here, 24 hours, or 48 hours discontinuous or continuous incubation. And it was more toxic on the adenocarcinoma cell line than on the fibroblasts. And we even quantified in terms of how much toxic it was, this type of nanoparticle. You see here in red, these are the cases of the incubations of cells. In this case, it's only cacodoe cell line. Incubation with irinotecan in solutions, let's say it's classical. And then here you see the irinotecan absorbed on the nanoparticles, either with folate or without. And we obtain, for instance, 7 times increase of irinotecan toxicity with respect to the irinotecan in solution. And even just for the folate nanoparticle itself of 1.3 times increase of toxicity. And of course, we looked again at these type of nanoparticles using our this microscopy system. We noticed, for instance, that when the nanoparticles were containing folate, the accumulation of these particles was seen as really bright spots. Even the material is silica-based, so it should not reflect a lot. And we identified, for instance, the wavelengths characteristic to the folate, to the combination of, to the irinotecan, to the combination of irinotecan, folate, and nanoparticle. And we observed that, for instance, the maximum attributed to the irinotecan at 550 nanometers visibly diminished due to the release of the nanoparticle during the 24 hours incubation. Yes. And then we saw that these nanoparticles are found in the close vicinity of the nucleus, in the shell around the nucleus, and in a quantity, in a number, which is significantly increased when the folate was present. So I will say that's my presentation, that's my talk. If you have questions.
Well, we are delayed, so I propose that we go to the coffee break. And
Sure.
Any question you take the opportunity of the coffee break to put to the presenter. Thank you so much. by Luciane Bahia. She comes from Faculty of Physics. Not she, but he comes from Faculty of Physics, Babes Bolyai University, Romania, with the title Composite Based on Biopolymers Bioactive Glass Ceramics, containing copper and gold.